Welcome to a deep dive into the fascinating world of fusion energy. We're going to be exploring how scientists are trying to, bottle a star to create a sustainable energy source right here on Earth. So, by the end of this deep dive, you'll understand the core challenges of fusion, the ingenious solutions being developed, and get like a glimpse into a future potentially powered by these mini suns we're talking about. Temperatures 100 times hotter than the sun's core, materials colder than interstellar space, and walls that breathe fuel, while withstanding the fury of a miniature star.
Yeah, it's remarkable how far we've come from the realm of science fiction.
Mm.
Fusion research has really made incredible strides, and the potential benefits are enormous.
Yeah.
Clean, nearly limitless energy with the power to really reshape our world.
It is remarkable, but also audacious. Like we're essentially aiming to replicate the sun's power source
Yeah.
in a controlled environment here on Earth. I'm curious, where do we even begin with such a task?
Well, at its heart, fusion involves forcing hydrogen nuclei together
Yeah.
with immense pressure, causing them to fuse into helium and release tremendous energy, the same process that fuels stars. To achieve this on Earth, we need to create incredibly extreme conditions.
Okay. And just how extreme are we talking about? Paint the picture for us.
So picture this, temperatures exceeding 100 million degrees Celsius,
Mm-hmm.
hotter than the sun's core. We also need immense pressure to bring those nuclei close enough for fusion to occur. These conditions create a state of matter called plasma, you can imagine it as, a superheated, electrically charged gas where electrons are stripped from atoms. Controlling that plasma is one of the biggest hurdles in fusion energy.
We're essentially creating the hottest thing in the universe. How do we even begin to contain something that hot without everything just vaporizing?
Yeah, that's where magnetic confinement comes in. We utilize powerful magnetic fields to contain and control the plasma, preventing it from coming into contact with the reactor walls.
It's fascinating how we're using some of the coldest technology to control the hottest thing. We can create.
It is a bit ironic, isn't it? We rely on superconductors, materials that conduct electricity with zero resistance, to generate these powerful magnetic fields. And for them to work, we need to cool them to near absolute zero. So you have this incredible temperature gradient, a scorching plasma mere meters away from materials colder than interstellar space.
That's mind-boggling. And what shape does this magnetic field take?
The magnetic fields shape the plasma into a torus, which is like a donut shape. There are two main designs for achieving this, tokamaks and stellarators. Tokamaks, which are used in the ITER project, are the most common. They use a series of magnetic coils to create a twisting magnetic field that confines the plasma.
Why have tokamaks become more common than stellarators? Is there like a specific advantage to them?
That's a great question. Tokamaks, while complex, are somewhat simpler to engineer than stellarators. They tend to be more stable and efficient at confining plasma, at least with our current understanding of plasma physics. Stellarators have their advantages, theoretically offering better long-term stability, but they present greater engineering challenges, particularly in achieving the precise magnetic field configurations required.
It sounds like we've opted for a design that's more achievable with our current technological capability. So, these magnetic fields contain the plasma, preventing it from touching the reactor walls. But what kind of material can withstand the incredible heat and radiation from a miniature star?
That brings us to the first wall, the unsung hero of the fusion reactor. It faces a barrage of challenges: withstand bombardment by energetic particles, manage extreme heat transfer, and even breed tritium fuel.
Breeding fuel. I'm intrigued. This wall seems to have a lot on its plate. Perhaps we can start with the particle bombardment. What kind of damage are we talking about?
Think of it as constant atomic sandblasting. Neutrons, helium nuclei, even stray hydrogen ions are constantly colliding with the wall, causing structural damage over time. This leads to erosion and potential weaknesses in the wall.
So it's not just about the initial heat, but also this constant wear and tear from the particles. What about the heat transfer? How does the wall cope with temperatures hundreds of times hotter than the sun's surface?
That's another crucial factor. The first wall needs to efficiently absorb this heat and transfer it to cooling systems. Otherwise, we run the risk of the wall literally melting. It's not just about being tough, it's also about being an exceptional heat conductor.
This wall is starting to sound like a superhero. You also mentioned tritium breeding. Can you elaborate on that?
Tritium is one of the hydrogen isotopes we use in fusion, but it's extremely rare on Earth. So the reactor has to make its own. The first wall plays a crucial role in this. It slows down neutrons released during fusion, which then interact with the layer of lithium placed behind the wall. This interaction splits the lithium atoms, producing tritium.
So The wall isn't just a barrier. It's an active part of the fusion process. It's like a self-sustaining ecosystem. But finding a material that can withstand particle bombardment, handle extreme heat transfer, and breed tritium must be a monumental task. What options are we looking at?
There's no perfect solution, which is what makes it so fascinating. Every material we consider has its own trade-offs.
It sounds like a classic scientific dilemma. What are some of the leading contenders in this material search?
One promising candidate is tungsten. It's incredibly strong, boasts the highest melting point of any metal, and doesn't retain radioactive tritium as much as some other materials. Plus, it has a low sputtering rate.
Now, I have to ask, what exactly does sputtering rate mean in this context?
That's a good question. Sputtering rate refers to how easily atoms are knocked loose from the material surface by the energetic particles. A low sputtering rate is crucial because we don't want tungsten atoms contaminating the plasma.
Tungsten sounds pretty impressive, but you mentioned trade-offs. What's the downside here?
The issue is that even a tiny amount of tungsten in the plasma can cause problems. Tungsten atoms have a lot of electrons, and those electrons can absorb energy from the plasma, re-emitting it as light. This cools the plasma down, making it harder to maintain the temperatures needed for fusion.
It's like a tiny energy vampire, sapping the heat from our carefully crafted plasma. What other materials are being explored?
Another contender is beryllium. It's excellent at multiplying neutrons, which is vital for breeding tritium. It also helps remove impurities from the plasma.
Beryllium seems like a strong contender. What are the drawbacks there?
Well, beryllium is toxic and has a higher sputtering rate than tungsten, meaning it erodes more quickly. It's also susceptible to damage from electrical currents induced by the fluctuating plasma. So while it's helpful, it's also quite fragile.
It seems like we have a tough but contaminating option, and a helpful but fragile option. Are there any other materials in the running?
Researchers are exploring the possibility of using boron. As a coating for the tungsten wall, boron could reduce sputtering and contamination. But it has its own issues. With tritium retention, this could make the wall highly radioactive over time.
Boron sounds promising, but the radioactivity is a valid concern. Are there any out-of-the-box ideas being tossed around?
There is one that's particularly fascinating: liquid lithium.
Liquid lithium. You mean the stuff in batteries? Are we talking about a reactor with a wall made of molten metal?
Precisely. It sounds radical, but it has remarkable advantages. Liquid lithium can't really be damaged structurally, and it actually helps the plasma reach fusion temperatures more easily. Plus, it can act as both a coolant and a tritium breeder.
A liquid wall that cools, breeds fuel, and can't be damaged. It sounds like something straight out of a science fiction novel, but I'm assuming there are challenges with liquid lithium too.
Of course. Containing and controlling a flowing liquid metal within a fusion reactor presents some significant engineering hurdles. But the potential benefits are so compelling that researchers are actively pursuing this concept.
It's incredible how each challenge leads to more innovative solutions. The sheer ingenuity in this field is inspiring.
I agree. And it's not just about finding the perfect material. We're constantly refining our understanding of plasma physics and developing new technologies to control and manipulate the plasma more effectively. It's a multifaceted challenge.
Speaking of the bigger picture, let's shift our focus to the progress of ITER and the exciting developments happening in the wider world of fusion research. I'm curious to hear about the latest updates.
ITER is indeed making steady progress. Though it's undeniably a long and complex project, they actually switched back to a tungsten first wall in 2023, after initially planning to use beryllium.
That seems Team Tungsten is back in the lead. Does this mean beryllium is completely off the table?
Not necessarily. They're still experimenting with various options for neutron multipliers to enhance tritium breeding. It's a delicate balancing act, maximizing performance while minimizing the downsides of each material.
It sounds like a constant game of optimization. What's the latest timeline for ITER? When can we expect to see it generating actual fusion reactions?
They achieved first plasma in 2025, a significant milestone. However, their first fusion reaction using deuterium isn't planned until 2035. And for their first commercial-grade deuterium-tritium fusion reaction, the kind that could actually generate power, we're looking at 2039.
2039. It seems fusion power is always on the horizon, yet somehow perpetually out of reach. Do you ever get a sense of, well, impatience with the pace of progress?
It's understandable to feel that way. Fusion has been a long and demanding journey. But remember, we're talking about recreating the power of the sun here on Earth. It's a monumental undertaking, and these things take time.
I suppose patience is a virtue. especially when we're talking about a technology with such immense potential. What about those smaller, private fusion companies we've been hearing about? Some claim they'll achieve fusion much sooner than ITER. Is this just hype? Or could they genuinely beat the giant to the finish line?
It's an exciting time to be following fusion research. There's a surge of innovation happening outside of the large government-funded projects like ITER. These private companies are exploring diverse approaches, some quite radical, utilizing lasers, magnetic fields, and even colliding plasma beams.
It sounds almost like a fusion race is heating up. It's like a science fiction movie plot unfolding in real time.
I suppose there's an element of that. Some of these companies are focusing on smaller, more modular reactors. That could be deployed more readily than a massive project like ITER. Their agility and willingness to take risks are certainly shaking things up.
Do you think these private ventures have a legitimate chance of achieving fusion power before ITER?
It's certainly within the realm of possibility. They're attracting significant investment. And that kind of environment
Yeah.
can foster incredible breakthroughs.
So, it's a bit like the tortoise and the hare, with ITER as the methodical tortoise, and these private companies as the nimble hares, each taking a different path to the finish line.
That's an apt analogy. It will be fascinating to see who, if anyone, reaches the finish line first. Or perhaps they'll both contribute to the ultimate goal of commercially viable fusion power.
Now, shifting gears a bit, let's zoom out and consider the broader implications. If we do succeed in cracking the code of fusion power, what could it mean for our world? What kind of future could it unlock?
That's the million-dollar question, isn't it? The implications are profound. Imagine a world powered by a clean, practically limitless energy source, a world free from dependence on fossil fuels, with significantly reduced greenhouse gas emissions.
It sounds almost utopian, a world without energy scarcity, where clean energy is abundant and accessible to all. But are there any potential downsides or challenges we should consider? Is it truly a silver bullet solution?
Of course, every technology, no matter how promising, comes with its own set of challenges. Even with fusion, we'll need to address issues like waste disposal, reactor safety, and the potential for misuse of the technology. Responsible development and implementation are crucial.
It's a reminder that technological advancements, while powerful, aren't inherently good or bad. It's how we choose to develop and utilize them that determines their ultimate impact.
Precisely. Fusion power has the potential to transform our world for the better. But it's our responsibility to ensure that transformation is a positive one.
It's a responsibility we can't afford to take lightly. But for now, it's inspiring to witness the remarkable scientific advancements happening in fusion research.
I agree. It's a testament to human ingenuity, our persistent drive to push the boundaries of what's possible and strive for a better future.
And it's a story that's still being written. Who knows what breakthroughs await us in the coming years?
That's the beauty of scientific exploration. It's a journey into the unknown, fueled by curiosity and the pursuit of knowledge.
Well, on that note of anticipation and wonder, I think it's time to wrap up our deep dive into the fascinating world of fusion energy. But don't worry, we'll be back next week. To continue our exploration, stay tuned.
Yeah, it's a question with almost limitless possibilities. It's like asking what humanity could achieve with a source of near infinite clean energy.
Exactly. Imagine the potential impact on society, the economy, our environment. We could see a world where energy poverty becomes a relic of the past, where industries are transformed by access to clean, abundant power.
Yeah, we could see a significant reduction in greenhouse gas emissions, offering a powerful tool in our fight against climate change and a chance to protect our planet for future generations.
Transportation could be revolutionized. Imagine electric vehicles powered by fusion, further reducing our reliance on fossil fuels and creating a truly sustainable transportation system.
It's not just about practical applications. Fusion energy could propel scientific advancements we can barely conceive of today. It could open up new frontiers in space exploration, materials science, medicine, and countless other fields.
It's truly awe-inspiring to consider the ripple effects this technology could have on every facet of our lives. It's both exhilarating and a bit daunting to think about the potential shifts we might experience.
It is. But I believe it's a future worth striving for. A future where clean, abundant energy empowers humanity to reach its full potential.
Well said. It's been a fascinating journey exploring the intricacies of fusion, from the immense challenges to the groundbreaking solutions and the tantalizing possibilities that lie ahead.
It's been a pleasure delving into this topic with you. The ingenuity and dedication of those working in fusion research is truly remarkable.
And on that note of inspiration and anticipation, will leave you to ponder the potential of a future powered by fusion. Thanks for joining us on this deep dive into the incredible world of fusion energy. Keep those minds curious. And until next time, happy exploring.
Yeah, and it's not just about the energy itself. It's about the geopolitical shifts, the potential for global collaboration. Imagine countries working together to build and operate these fusion power plants, sharing resources and expertise.
Yeah, it's like a
Yeah.
unifying force for humanity, a common goal that transcends national borders. And speaking of borders, what about space exploration? Fusion could be the key to unlocking interstellar travel. Imagine spacecraft powered by fusion engines, reaching distant stars and planets.
Absolutely. It could completely revolutionize how we explore the cosmos. We could reach destinations that are currently unimaginable with our current technology.
It really paints a picture of a limitless future where energy is no longer a constraint, but a catalyst for progress and innovation.
It's a future where we can finally break free from the limitations of our current energy sources and truly unlock our potential as a species.
Well, on that note of optimism, I think it's time to wrap up our deep dive into the world of fusion energy. It's been an incredible journey, exploring the science, the challenges, and the boundless possibilities. Thank you for joining us, and until next time, keep looking